Good afternoon, good afternoon. Welcome whenever you are in Warsaw, Gdańsk, Huelva, San Francisco, whatever, whenever in the world. So today I will talk about Yang-Baxter equation, Yang-Baxter operators, but with relation to not Tory. So first, few words about Yang and Baxter. Yang was born in China in 1922. Then he went to America and did PhD in Chicago under Edward Teller. I mentioned this because Teller was professor of physics at GW for a while at George Washington University. Then Yang got Nobel Prize in 1957. Then Rodney Baxter is younger, was born in 1940 in London, and he then went to Australia and was distinguished professor there and is now professor emeritus in Australia. Connection between Yang-Baxter operator and not Tory was discovered by von Jones, I think in 1985, 1 year after he discovered his famous Jones polynomial, and he found that there is Yang-Baxter operator which is giving Jones polynomial. I will talk about this today. And maybe I should mention that the name Yang-Baxter equation operator was relatively new. It was given by Faddeev, Petersburg-Leningrad School of Mathematics, of Mathematical Physics. Before it was very often called white triangle equation. So with this, I will go back to not Tory. So we discussed in this place already rather easy invariants of rings, but very nice. Fox coloring, fundamental group, Alexander polynomial, and all of them could be defined by coloring. So consider crossing of the diagram. We are back in not Tory. So I'm using even orientation, so this is positive crossing. So it was just by coloring arcs and doing some constructions. So very naively we can make it still much more general. Remember, today we do it very naively, but in kind of big generality. So what we need for this? We need set of colors. With this set of colors, we'll be coloring, we call this semi-arcs of the diagram, meaning that we can change color even if we go over. So semi-arc is from crossing to crossing. So we need such colorings. So phi is function from semi-arcs into x. So every semi-arc has color. Let's say here has color A, color B, color C, and color D. I'm using convention that we go from top to the bottom. So what about this? In Fox coloring, remember that or other invariant, there was some rule that we know what is D when we know AB, we know what is C when we know AB. It was already in more general setting. But here we try to be much more general. Like we say what is probability that this situation happened? It will be not really probability. Our weights can be negative, can be bigger than 1, but we can think a little. What is the chance that it happened? So put this weight. R, A, B, C, D. This is just notation. If color here is A, here B, here C, here D, we put weight R, A, B, C, D. This may be integer Z2 or any general ring, commutative ring. Let's call this K. Okay, now just to remind you how before we were constructing invariant, even more naively. When here was A and B, C and D was uniquely given. There was a rule. So if coloring was not satisfying rule, weight was 0. If it was satisfying rule, weight was 1. Here we allow more generally. But then what? How to construct invariant? If at least at one crossing weight was 1, or was 0, then it should be not allowed coloring, which means it should be 0. How to achieve this? We just take product of our weights. Product of R, A, B, B of crossing V. If it is allowed, it is 1. If it is not allowed, it is 0. And then we counted number of colorings, allowed colorings. Here we have to just, over all colorings, we have to add weight. Before it was either 0 or 1, and if it was 1 was counted, if it was 0 it was not allowed coloring. Here we have this such colorings. So such functions. Now we should be slightly more general. Why? Because I draw here positive crossing, but we can have different rule for negative crossing. Let's do this. So I don't need this small piece, so let's draw here negative crossing. So it should be similar. For negative crossing, if here is A, B, and here is C, B, then let's call this weight R bar, A, B, C. For a moment there's no relation between them. But then in this sum of products, because it may be negative crossing or positive crossing, this V, then, so the V is crossing. Then let's put this tilde. For positive crossing, tilde is R. For negative crossing, tilde is bar. So we'll consider such sums. They are very well known in physics. So weight is called Boltzmann weight from statistical physics. Then we take sum over products of Boltzmann weights. State sum, so called. So this is kind of taken language from statistical mechanics. So now what we do next? As in knot theory, we have some number associated to diagram. Now we should check Rademacher moves. So I will erase this, and then we check first, second Rademacher move and third Rademacher move. What about first Rademacher move? First Rademacher move sometimes needs some balancing. There's a very nice paper by Vladimir Turayev when he's showing that essentially it is enough to consider second Rademacher move and third, and balancing always he was successfully showing how to do. I should add more that was von Jones who was first finding Yang-Baxter operator, we are not yet there, Yang-Baxter operator giving Jones polynomial and the generalization Humboldt polynomial. As promised, we'll check now second Rademacher move and then third. So I will consider Rademacher move, second one. So this must be equivalent to this. In oriented case, there is, sorry, that was not Rademacher move. This. So we know that essentially if we orient this, there are two Rademacher moves. So I will consider here the case when both of them are going down. And mention that really there is no need to change Rademacher move when they are oriented anti-parallel because of well-known theorem of Alexander that every ring can be changed into braid, and then for braids there is so-called Markov theorem from 1936, which essentially for us at least say that it's enough to use third Rademacher move and with all positive crossings, and second Rademacher move when strings are parallel. And then there's first Rademacher move, which I said I will ignore today. So let's see what happened. Just remind you that we have here, if here have A and B, then we have R, weight and weight, weight for positive crossing, weight for negative crossing. This would be difficult to see, to do this in coordinates. So how we do? We just think a little. We have once more, let's draw for positive crossing. What we're saying that if here is A, here B, here C, and here D, then you have weight L, I, A, B, C, D. So maybe it's difficult to analyze this because we have these coordinates and we plenty big sums, etc. But let's see, we can really easily code this using linear algebra. Namely, we can think that really pairs A and B are bases of some linear space or maybe module, and then these are coordinates, these are entries of the matrix giving this map. Let's be more precise. So we can interpret this Boltzmann weight and this notation as a map, let's call this R, from set of colors, now these are basic elements, pairs. So, in fact it's not this because we can have linear combinations. So maybe some small notation will be easier with small notation. As I said, we have modular linear space where X is the basis. So we write like this, and then the map is going from V tensor V into V tensor V. Or more naively, we have to say on the basis, we take pair of colorings A and B, and it goes to linear combination of pairs. So now, how to change these weights into map? We just say that R of AB is the sum over all CD, R CD, R AB CD, CD. Instead of tensor product, I'm writing pairs because it's on the basis. So this is really what is the meaning, how to change Boltzmann weights into, maybe that's times, this is coefficient, not function. So this is how it works. So now we see that we can change all our maps. Instead of coordinates, we can just say that on every crossing we do R. So here we do R, but here will be the second matrix because this is negative crossing, will be R bar. Now it became very easy because we like the composition of R and R bar be identity. If we draw this on the other side, will be second identity. So what we get from Rademacher move is that R bar is equal to identity is equal R bar R. Here is one of them, first R then R bar. So what it means? That to have the second Rademacher move when strings are parallel, we need R to be invertible, and in fact we need that R and bar R are inverse one to another. So here's of course R is mapped like this, but R bar as well. We have two maps, R and R bar, and second Rademacher move is telling us that R is invertible. Let's check what happened with the third Rademacher move. With the third Rademacher move, but of course we have to use our language, otherwise equations are very complicated. Sometimes we have to go to equations, and in fact you will see maybe today some calculations, and you have to work a little with coordinates. Okay, third Rademacher move, I will draw a big picture. 1, 2, 3. This is one side of third Rademacher move, and then this goes to the top. Third Rademacher move, it is not Yang-Baxter, it's Rademacher move. And then 1, 2, 3. So now this is first, this is second, and this is the third one. So this is the third Rademacher move in the blade form. Remember that every crossing is positive because we go down. Not on every crossing is possible, but it's enough to analyze this situation and then use Markov theorem. Okay, so now let's see, what is our map? Our map is really from three copies. So it is mapped from V tensor V tensor V into V tensor V tensor V. So, what is map on the, and they should be equal, map on left side and map on right side. So, what are these maps? Having this nice language of linear algebra, we can say we go from top to the bottom, we apply here R, crossing is positive, and here just identity. Then on the next level, here we apply R, and here identity. And finally, in this level, here is R, and here nothing happened. And here identity. Okay, what we got on this side? We don't have even to decide whether we read symbols from left to right or right to left, because symmetric. So we got R cancel identity, composed with identity cancel R, and finally R cancel identity. So now what will happen on the other side? Similar thing, except that first we start from identity R. Then we have R identity. And then identity R. So once more, we are comparing map from the top to the bottom, and you like to have the same effect. So here output should be the same, and here from this we get identity cancel R, R cancel identity, identity cancel R. And they should be equal. So to have invariance of our state sum under the third Rademacher move, we need this equality. This is exactly famous Yang-Baxter equation. So now, such operator, so R, remember, was going from V cancel V into V cancel V. So such operator is called Yang-Baxter operator if it is invertible, needed for second Rademacher move, and satisfy Yang-Baxter equation. What if it is not invertible? Sometimes it's useful, and you will see later that when I define homology, we don't need really invertibility. So maybe let's see terminology. R is pre-Yang-Baxter operator, Yang-Baxter operator if Yang-Baxter equation holds. And just to add, if additionally R is invertible, then we call this Yang-Baxter operator. So, how to use this in not only in more delicate way than just sum over all products of weights. This is relatively new. So this for general Yang-Baxter equation, it is really Victoria Lebet. Maybe her name should be here. Lebet. And so this is the year 2012. So next I will tell a little about homology and maybe I will find concrete example. Before I will go to homology, I should remind you or describe what was the Jones Yang-Baxter operator, which is giving Jones polynomial, or maybe more generally, what is Yang-Baxter operator giving more general Humphrey polynomial. So let's first the one which is giving Jones polynomial. This I can write quickly in basis. So let our X will have two elements. So X, two elements. V is equal, of course, K of X. And K will be a ring of polynomial, usual ring of polynomial of one variable Q. And what is Yang-Baxter? A matrix operator, but in this basis, it will be something like this. It is, of course, V tensor V is 4-dimensional. So maybe I should write really 0 tensor 0, 0 tensor 1, 1 tensor 0, and final 1 tensor 1. In this basis, here will be the same. What is the matrix? Let's put Q here and Q here, and then in the first row, all the rest is 0. In the last row, everything is 0, and 0, and 0, and 0, and 0. You have to just fill inside. So here in convention, they use it as Jones matrix. It is Q minus Q inverse 1, 1, 0. So this matrix is giving Jones polynomial. I will not do this here. Just I would stress that really this matrix, first of all, it is invertible. Secondly, minimal polynomial is of second degree. This is not so difficult to check. Nice exercise. And then because of this, it is giving relation which in not only relates three links like this. Linear relation between polynomial associated to them, we think is related to minimal polynomial of this matrix. But here I'll do purely algebra. So how to generalize this? So we call this level 2 Jones polynomial. More generally, it's better probably to give this by equation, by formula. So R, A, B, C, D is equal, and we have values, possibilities. So I usually help myself looking at small picture. A, B, C, D. Why I find this picture useful? Because I know from not theory that either color go true or color go smoothing, but there is no other possibility. Always, otherwise, if set A and B is different than C and D, then we get 0. So let's say, consider first non-zero situation. This is generalization of this. So we have Q. Q is when really we go true. This is the case when everything is equal. Yeah, Q is A equal B equals C equal D. Now, when we get Q minus Q inverse. So now, I didn't say what is X. Here X has 2 elements, I said level 2. Now X has M elements, level M. But what is important that these are colors which are ordered. We know which number is bigger, which is smaller. So this Q minus Q inverse, kind of when we smooth this. So if A equals C, less than B equal D. What is left? When it is 1. It is 1 when we go through, but with different colors, not the same color. So going through, meaning that A is equal to D, A is equal to D, A is equal to D, and I did a mistake already, because here should be Q. So, I will check in a moment. So if A is equal to D, less than B equals C, that's Q. And it is 1 when A equals D, greater than B equals C. Still it corresponds to smoothing, so A equals C, B equals D, and 0 I will write otherwise. There are two cases, but the most important case is when set A and B is different than, say, C and D. And I should admit, my memory left me for a moment. In this place, there's 1, not Q. So I collected this as well. 1. And when you put Q equal 1, then it should be just switch. Color A go is D and B equals C. So whether here was 1 or Q, it was working well. But this is the proper Yang-Baxter operator or matrix on Yang-Baxter operator in giving Jones polynomial. This is giving for values different, and these are different substitution in home-flipped polynomial. So eventually, so let's say Jones, and this is home-flipped. So Jones was giving talks about this, and Turayev was in audience, and then he generalized this idea and wrote a very nice article. I suggest you to look at it. Well, just every Yang-Baxter operator, he was kind of natural Yang-Baxter operator, is giving invariant of links. In fact, it's not totally true. It satisfies third Rademeister move, second Rademeister move, but first Rademeister move, each time you have to kind of work independently, balancing this. So first Rademeister move is preserved. So what I will do now or later is to compute homology of such Yang-Baxter operator, or more generally partially of this Yang-Baxter operator. But this will be later, and this is rather technical. First, I should really remind you what is really homology, or in particular, how we define homology for Yang-Baxter operator. So very shortly homology. So when we have sequence of modules, and by convention we go down by 1, and we have maps between them. This is called chain complex if composition bundle n plus 1 is 0. So that's chain complex. Then homology, because here kernel is bigger than the image, we can define an homology of chain complex as kernel of this, or of this map, bundle n, divided by image of this. N plus 1. So this is just definition. To define homology of Yang-Baxter operator is useful to have some more concrete thing. We call this, slightly changing the name given to this by Eilenberg, we call this presimplicial set, or more generally presimplicial module here. In presimplicial module, our bundle operation is broken into pieces. Kind of simplex and bundle of the simplex is composed of pieces. So this algebraic analog. I equal 0 to n minus 1 to I d I. And then, to have bundle operator satisfying condition of chain complex, we have the following condition. So let me write this. So to get chain complex, we need di dj is equal to dj minus 1 di for I less than j. I will call this presimplicial module. So presimplicial. But really, in not totally more often, we have our spaces glued not from simplices, but from cubes. For cubes, by convention, this is broken. Cube has top and bottom, so it will be not one map, but two maps. And additionally, in cube, In simplex, n-dimensional simplex has n plus 1 vertices, so we count from 0 to n. For cube, n-dimensional cube has n pairs of parallel faces, pairs but n only. So similar construction will be similar definition, but for cubic, precubic will be that this is the sum of I equal 0. It's not from 1, as I said, from 1 to n minus 1 to I, and I will call this di left, I will explain later, minus d1 right. Kind of on the cube, I think left side and right side instead of top and bottom, but doesn't matter. This will be definition, and when it produces chain complex using this definition, we need similar equation like this, but we allow here epsilon delta left or right, and here should be delta epsilon. Nothing more. Such structure with many operators like this, map from Cn to Cn minus 1, satisfying these things is called precubic module, and if you define bundle operation in chain complex using this formula, it will produce homology, produce chain complex and homology. So just write this precubic module. Okay, I wanted this definition to be very short, so how we can define such precubic module from Yang-Baxter operator. So one should be a little careful, but first general scheme. So I said more or less 8 years ago, I discovered this, and Victoria Lebet discovered this independently. However, of course, we're both motivated by homology of quantles and then of homology of biquantles. So Fenn, Sanderson, Carter, Kamada, Saito. So let's make picture which will explain how I have this precubic module from Yang-Baxter operator. Amazingly simple. Remember, I need left and right. Okay, precubic module from, in fact it's enough to have pre-Yang-Baxter operator. Invertibility is not needed initially. From I. Okay, the following picture will explain. So, first of all, of course, we should know what is Cn. Cn will be just whatever link we work, k of x to power n. Remember, x was set of colors, base of linear space for Yang-Baxter operator. So Cn is k of xn, and we need di left and the di right. Okay, the following picture. The wall, some module, but I will not need this. And then we have n points. And here is I, etc., etc. So what we do? From I go directly to the wall, and all other are going through. So clearly we are losing one thing. So this will be, and how to interpret this? We start from this product. Maybe I should say that it is the same as V tensor n times. So I start from, but I can say everything is x, basic element. So I start from x, 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 x. But now I apply at every crossing our Yang-Baxter operator. This is some module, left module. This for our theory will be not needed. And then the same on the right. Except that I will have all crossings positive, so on the right, so this is DLI. And this is what is DI right. Similarly, except that the wall, this module right is here, and then it's going over, because it will be positive, over this, which is disappearing on the wall, and then going straight. So this is DIR. So you can ask, what is this? And maybe I will just recall what Victoria checked. For me, I prefer this to disappear, because later I try to produce so-called coscycle invariants from Yang-Baxter operator. Kind of, I don't have place for wall, at least I don't know how to do this. Maybe some equal or something in space, and there's having place of wall, but I don't know. So I have to assume that our matrix, Yang-Baxter matrix, is column unital. So in particular stochastic, but it is enough, it's column unital. Then I don't need wall, just this disappear. But let me write axiom, which very easy axioms for precubic module which Victoria Levet gave. So what is this map? It is map ML tensor V into ML. Kind of we hit wall, so we are left with wall only. And what it should satisfy, from the left side, right will be similar. It should satisfy something like this. If you hit one and then another, it should be the same as first you hit with this, cross and hit with this. And similar axiom on the right side. Why the strange axiom? Very easy to check that to have pre-cubic module, you need this, just from definition. And otherwise, the fact that we get pre-cubic module follows from braid relations, or our Tertra-de-Maistre. So probably I should not do more with definition. This should be kind of clear. I think it's a good idea. So now, of course, the goal is to have some interpretation of this homology in not Tori, this generalized coscycle invariant, and then eventually connect with Hovanov homology, and then even better, to have Hovanov homology should have some meaning in phase transition of some statistical mechanical systems. This is just the dream. So what should be done here? I think I should say that we try to make our matrix column unital. This we need, then we can forget about walls, does this disappear? There was n tuple, and then we have linear combination of n-1 tuple, and whatever was here disappear. So column unital. So we need R, matrix of R, column unital. Then there's no problem. But let's recall what was matrix given for John's polynomial, or more generally Homflick polynomial. It was not column unital. So with my student Xiao Wang were experimenting. I said, let's check what happened when you make just artificially take this Yang-Baxter operator, Yang-Baxter matrix, and may by force kind of flatten this to column unital matrix. So let's do this here. Let me erase everything here. So I hope now I can repeat this matrix level 2, John's polynomial. It was Q 0, 0, 0, 0, Q minus Q inverse 1, 0, 0. Remember, this is 1, 0, 0, and finally 0, 0, 0, Q. So what we have to do, we have to divide, to try to divide, to get column unital. Divide first column by Q, no problem. 1, 0, 0, 0. Second column adds to 1 plus Q minus Q inverse. So it will be more involved, because you have to put this denominator. So it will be Q minus Q inverse divided by 1 plus Q minus Q inverse. Then will be 1 over this, 1 plus q minus q inverse, finally 0. And here nothing, it was already 1. And here q will change to 1. Okay, we have new matrix, look like little arbitrary. So it was very pleasant thing to realize after first Xiao1, and in fact Adam Sikora independently, when I asked them, checked that really this is still Yang-Baxter operator. And then when you try to prove this without computer, it's not difficult as well, in this case and in more general case of any level, as I wrote before. So now just notation we'll be using, we'll just make some substitutions. So we put y squared is equal 1 plus q minus q inverse. So with this substitution, final our matrix, which we'll be using for, and Yang-Baxter operator we're using to compute homology for n equal 2, but will be almost the same in general case, because normalization is similar. So what will it be? 1, 0, 0, 0, 0. What is this? It is y squared. We add 1 and minus 1. So this will be 1 minus y squared. I can make mistake. 1 minus y squared. 1, 0. Then 0. This by definition is y squared. 0, 0, 0, 0, 0. So this and its generalization will be the matrix for which we studied homology, which I just defined before. And it is non-trivial, and we computed H2. Generally, we have conjecture for any homology, but for n equal 2 level, this one. In generally, we have guess what is this for n equal 3, and in fact we have joined project with, of course, Xiao, my co-author, I should write his name, so, a student, and with Saito and Mohamed Al-Mhahadi. So this is project, compute H3, but you computed in full generality H2. And this is more technical thing, which I will describe later. Thank you.